Welcome back. This is the second video of the Crystal Clear Electronics 2 curriculum, Chapter 13. In this video, we'll look in detail at some sensor types, but first, it's important to mention something about how sensors work that we've missed from the latest video part.
What have we missed?
In the latest video, I have mentioned that the input and output of the sensor are proportional to each other, and I would like to elaborate on this a little. The relationship between the output and the input of a sensor can be specified in several ways, for example, in tabular form, graphically, or by a function. The use of so-called static transfer characteristics is common. The figure is the static transfer characteristic of an idealized mass flow meter. The horizontal axis shows the physical signal as x at the input, and the vertical axis shows the electrical signal as y at the output. The units of measurement of the axes are determined by the physical signal and the electrical signal respectively. Consequently, for the sake of generality, no units of measurement are shown in the figure. The static indicator indicates that this curve is interpreted with a very slowly varying input. The reason for this is that the sensor cannot immediately follow the change in the input. It has some response time. Knowing the static transfer characteristics of the sensor output allows the physical signal input to be determined and is therefore crucial. Another important characteristic of the static transfer characteristic is the slope of the curve. The slope of the curve for the point x0, y0 is shown in the figure. The slope shows the change in y for a change in x, which is the sensitivity of the sensor.
The larger the slope, the more sensitive the sensor is to a change in input. It is also possible that the slope is 0, so the same value of y is associated with several values of x, thus the sensor is insensitive to changes in input in the given range. This section of the static transfer characteristic is called the dead zone.
Now that it is clear to us, we can move on to the main topic of the video, which is the common types of sensors. Which one should we start with?
I think we should start with one of the most common types of sensor, the current measuring sensor.
Okay, let it be. When using the current measurement sensor usually, the aim is not to measure the current flowing through a conductor, but to measure the current flowing through a piece of equipment. For example, when measuring the consumption of an electric motor or the load current of a battery. An obvious solution is to measure the voltage across a resistor of known value. Knowing the value of the resistor and the voltage across it, the current of the resistor can be calculated according to I equals U over R, or Ohm's law. The analog-digital converters familiar from previous chapters can be used to measure the voltage, as shown in the figure. The AD converter of a microcontroller can also be used for the measurement, with appropriate signal level matching, but of course there are also target ICs for this task. In order not to significantly increase system losses, the resistance of the meter resistors is typically small. The current figure shows such a current measuring resistor. Because of the small resistance value, it is conceivable that the voltage to be measured will be in the millivolt range or less. For this reason, it is sometimes necessary to use an amplifier stage before the AD converter. This is included in the target ICs. The accuracy of the measurement is affected by the accuracy of the resistance value. Another factor affecting accuracy is the temperature dependence of the sensor.
Another way to measure current is to use a Hall sensor based on the so-called Hall effect. This latter sensor, which works on the magnetic principle, is described in detail in the 23rd chapter of the Crystal Clear Electronics 1 curriculum. We will not go into details, but we should also mention that other sensors, typically based on inductive principles, can be constructed for measuring alternating current.
Moving on to mechanical sensors, let's get to know the pressure sensors. The heart of such a sensor is an element that deforms or moves in response to the pressure. The amount of deformation or displacement can be measured and used to calculate the pressure. The two main types of pressure sensors are absolute and relative sensors. There are many possible designs. The pressure range and the expected accuracy will determine which type of sensor is appropriate. In many industrial applications, mechanical pressure gauges, known as bourdon tubes, are used to measure not only air pressure, but also to measure the pressure of any gas or liquid. By increasing the pressure inside the tubes, they gradually straighten out. This deformation can already be measured, for example by relating the displacement of the ends of the tubes to a potmeter by means of a clever mechanical solution, thus reducing the pressure measurement to a resistance measurement. Bourdon tubes can be used in different pressure ranges depending on the mechanical properties of their material. There are many pressure sensors in which the element that deforms in response to pressure changes is a plate or diaphragm, as we can see in this figure.
By definition, when a body is subjected to external forces, a mechanical stress is induced inside the body, which can be interpreted as the ratio of the force applied to the surface area exposed to the force, using a formula P equals F divided by A. Thus, the mechanical stress is of pressure dimension, which is Newton per square meter. A special case of the mechanical stress gauge is the strain gauge, which is used specifically to measure longitudinal variation.
Piezoresistive sensors also come in handy in pressure sensors. The diaphragm is stretched by the pressure difference, and this stretch is converted by the piezoresistive materials into a measurable change in resistance. This arrangement is illustrated in this figure in an absolute pressure sensor. The sensor is absolute because the pressure of the upper compartment relative to the vacuum determines the amount of deformation of the diaphragm.
Other sensors trace pressure measurement back to the measurement of electrical capacitance. If the deformable element and the surrounding casing are made of conductive material, capacitances, so-called capacitors, are formed there to store electric charge, since the deformable element and the casing act as the plates of the capacitor. The capacitance of a capacitor is inversely proportional to the spacing of the plates, so you can infer the amount of deformation from the change in capacitance.
I will not discuss the details of measuring the electrical capacitance here, for which a time-varying voltage is conveniently used. Here, you can see the block diagram of a relative pressure sensor based on the capacitive principle, but an absolute pressure sensor can also be made using this principle. The sensor is relative because the pressure that we have indicated with P1 and P2 can vary in both compartments. The amount of deformation of the diaphragm being determined by the difference between the two pressures.
Resistive or capacitive pressure sensors are often made in the form of so-called microelectromechanical systems, which you can hear more about in the following.
Still talking about mechanical sensors, a common operating principle of liquid-level sensors is that part of the sensor floats on the surface of the liquid, and the position of this floating body is measured. Tracking the position of the floating element can be achieved, for example, by mounting a magnet in the floating element and tracking its position with magnetic proximity switches, also known as reed relays. The system can then indicate predetermined fluid levels.
You can learn more about the reed relays in Chapter 23 of the Crystal Clear Electronics 1 curriculum. Instead of relays like this, it is now common to use Hall sensors that can sense magnetic fields. These sensors have already been used in current measuring sensors.
An interesting solution is an ultrasonic liquid level measurement, which estimates the distance of the liquid surface from the sensor from the time between the emission of the sound wave and its reflection.
In some cases, it may be necessary to measure the flow rate of liquids or gases. For this, it is a common method to measure the motion of an element moving with the medium.
This could be a paddle wheel or a turbine screw. The time it takes for the rotor to make a complete revolution is an indication of the flow rate. The rotation time can be measured, for example, with the previously mentioned Hall sensor, which is implemented by measuring the rotation of a magnet attached to a turbine.
The biggest advantage of this solution is its simple design, but it also has several disadvantages. The moving parts wear out with use and need to be replaced over time. And the inertia of the turbine means that it cannot pick up the speed of the medium immediately, so the sensor has some response time.
Exactly. There is also another disadvantage of this setup. It does not measure arbitrarily small flow rates, and there is a threshold below which the turbine does not rotate, but the fluid simply flows between its blades. Another measurement approach can provide a solution to these problems when influencing some physical properties of the flowing medium, so a conclusion can be drawn about the flow velocity. A common solution is to heat the medium, since the temperature change due to heating is related to the flow velocity. A device working on this principle is called a thermoanemometer. In general, the flow rate of the medium can be estimated from three parameters: the temperature of the medium, the amount of heat input, and the medium temperature after heating. It would be hard to keep all this in mind, so let's look at a diagram. In the arrangement shown in the figure, T0 measures the temperature of the incoming medium, and Ts measures the temperature of the heated medium. It is important to thermally insulate the temperature sensors from the pipe wall and to establish good thermal contact with the flowing medium. Thermal anemometers have the advantage of sensitivity, short response time, and no moving parts. There are many other anemometer designs. MEMS designs are also common for flow meters.
Microelectromechanical systems, abbreviated as MEMS, are micrometer or millimeter-sized systems that contain both mechanical and electrical components that work closely together. Because of their small size, sensors are preferably made in the form of such systems. A variety of materials are used in the manufacture of MEMS devices, for example glass, ceramics, polymers, and metals, but silicon and its various compounds are predominant. One of the main reasons for this is that silicon is a universal material. It has good semiconducting properties, making it ideal for making electrical components, but it can also be mixed with different materials to create good insulators or parts with good mechanical properties. And its manufacturing technology is sophisticated for making integrated circuits.
The direct transducer part of MEMS sensors uses piezoresistive, piezoelectric, capacitive, optical, and resonant measurement principles, among others. We will shortly discuss the capacitive sensing method soon. The optical and resonant techniques are mentioned for completeness only and will not be discussed in detail. Capacitive sensors work on the basis that the capacitance of a capacitor changes when it is moved. This can happen either by the plates of the capacitor moving relative to each other, as we can see in the first two figures, or by the dielectric that is moving between the plates, as you can see in the third figure. A differential capacitive sensor can also be made. In this case, the common arm, marked with Y, of two capacitors is displaced, so that the effect of the change can be measured in the capacitance of two capacitors C1 and C2. This principle can be used, for example, to make a relative pressure sensor, which we have already talked about at the beginning of the video. As an example, the MEMS implementation of the pressure sensor, already discussed, is shown in these figures. The left figure shows a simplified cross-section of the sensor. Above is the diaphragm, below is the cavity in the sensor, and below this is the sensor housing and the aperture in it. The sensor can measure the difference between the pressure values P1 and P2 using piezoresistive sensors, with resistors R1 and R2 embedded in the silicon membrane. In principle, one sensor could be sufficient, but using two sensors and clever measurement techniques, the sensor can compensate for the elongation caused by temperature changes that would introduce error into the measurement.
Sensors for force, pressure, mechanical stress, acceleration, orientation, which are known as gyroscopes, and flow are also commonly produced in MEMS form. Good examples are the accelerometers, gyroscopes, and microphones in smartphones, which are MEMS sensors. The latter can be considered a special case of pressure sensors, since in the case of the microphone, the sound waves are measured as a change in pressure in air. For more details on MEMS gyroscopes and accelerometers, you can check Chapter 23 of the Crystal Clear Electronics 1 curriculum.
In this video, we have looked at the operation and use of different types of mechanical sensors, but there are many more sensor types to come. After a short break, we will continue with these in the next video.
We'll start with light sensors, and we will also cover the different kinds of thermometers there. You definitely shouldn't miss the next video.
Bye.